Time doesn't flow the way you think it does. Richard Feynman discovered something so strange about time that it won him a Nobel Prize, and most people still don't understand what he actually found. What he revealed wasn't just a mathematical trick. It was a fundamental truth about reality that breaks everything you thought you knew about cause and effect, about past and future, about the very nature of time itself. Here's the paradox. An electron moves through space. Simple, right? But according to Feynman's work, that electron doesn't just move forward in time. Sometimes it moves backward. Not metaphorically, not as a mathematical convenience, actually backward through time. And when an electron moves backward through time, we see it as something else entirely. We see it as antimatter. Let me be clear about what I'm saying. Feynman proposed that a positron, the antimatter version of an electron, is literally an electron moving backward through time. Think about that. The same particle, just traveling in the opposite temporal direction. And this isn't speculation. This idea is built into the mathematics of quantum electrodynamics, the theory that describes how light and matter interact. The theory Feynman won the Nobel Prize for developing. But wait, if particles can move backward in time, doesn't that create paradoxes? Doesn't that violate causality? Doesn't that mean the future can affect the past? Yes, and that's exactly what makes this so profound. The universe doesn't work the way your intuition insists it should. Time at the quantum level is not a one-way street. It's something far stranger. Let me start with what Feynman was trying to solve, because understanding the problem makes the solution even more remarkable. In the 1940s, physicists were stuck. They had quantum mechanics, which described particles beautifully. They had relativity, which described space and time. But when they tried to combine them, when they tried to describe how electrons and photons interact at high speeds, the math exploded. Literally, they got infinite answers. Nonsense. The equation said that an electron's mass should be infinite, that its charge should be infinite, that everything should be infinite. Obviously wrong. Scientists tried everything. They tweaked the equations, adjusted the assumptions, invented new mathematical tricks. Nothing worked. The infinities kept appearing. It was a crisis. The theory that should describe the most fundamental interactions in nature was completely broken. And then Feynman had an idea. A crazy idea. An idea so simple and so radical that it changed everything. He said, "What if we stop thinking about particles moving through space and time as a single path? What if, instead, a particle takes every possible path simultaneously? Every path, all at once. The electron goes straight. It zigzags. It loops back. It goes backward in time, forward in time, sideways through dimensions you can't even imagine. Every single possibility happens." Now, you're thinking that's absurd. If a particle takes every path, how does anything happen? How do we see the electron go from point A to point B? Here's Feynman's genius. Each path contributes to the final outcome, but they don't all contribute equally. Each path has a certain probability, a certain amplitude, and when you add up all the amplitudes from all the paths, most of them cancel out. They interfere destructively. The crazy paths, the ones that loop around or go backward, they mostly disappear when you sum everything up. But not entirely. Some of those bizarre paths survive. Some of them contribute. And that's where the magic happens. Because those paths that include backward time travel, those paths where the electron becomes a positron for a moment, those paths are necessary to make the math work. Without them, you get the wrong answer. With them, you get nature. Let me show you what I mean with a concrete example. Imagine two electrons approaching each other. They repel. You learned this in school, like charges repel. But how does that actually happen? One electron has to somehow know the other electron is there. They have to communicate. And they communicate by exchanging a photon. One electron emits a photon, the other absorbs it, and the momentum transfer causes them to push apart. But here's the problem. If you calculate this process using normal quantum mechanics, you get the wrong answer. The calculation doesn't match experiments. It's close, but not exact. There's a correction, a tiny additional effect that the simple picture misses. And when Feynman calculated this correction using his path integral method, accounting for all possible paths the particles could take, including paths where time runs backward, he got the exact right answer. Perfect agreement with experiment. Why? Because some of the paths involve one electron briefly traveling backward in time, appearing as a positron, and then coming forward again. These paths contribute to the interaction. They're part of reality. And if you ignore them, your prediction is wrong. Now watch this. Feynman didn't just use this idea for electrons and photons. He developed a complete framework, a new way of doing quantum mechanics. He invented what we now call Feynman diagrams. These are pictures, simple drawings with lines and vertices that represent all the possible ways particles can interact. And in these diagrams, time runs vertically. Particles moving up the page are moving forward in time. Particles moving down the page are moving backward in time. An electron going forward in time is drawn as a line with an arrow pointing up. A positron, the antimatter particle, is drawn as a line with an arrow pointing down. But here's the key insight. They're the same line, the same particle, just moving in different temporal directions. An electron moving backward through time is indistinguishable from a positron moving forward through time. They have the same mass, the same spin, opposite charge, exactly as you'd expect if time reversal flipped the charge. This is not just a mathematical convenience. This is Feynman telling you something deep about reality. Antimatter is matter moving backward through time. That's why antimatter exists. That's why it has opposite charge. That's why when matter and antimatter meet, they annihilate. They're not destroying each other. They're cancelling temporal directions. One path going forward meets one path going backward, and they both disappear in a flash of energy. Let me tell you about the moment Feynman realized this. He was a graduate student at Princeton, working with John Wheeler, his PhD advisor. They were discussing the problem of self-interaction. An electron creates an electromagnetic field, and that field affects the electron itself. It's like the electron is pushing on itself. And when you try to calculate this, you get infinite answers. Wheeler suggested something radical. What if there's no electromagnetic field at all? What if the field is just a mathematical convenience, and what's really happening is that electrons interact directly with other electrons, including their future and past selves? Feynman took this idea seriously. He worked out the math, and he discovered that if you allow particles to interact with their own past and future, the infinities go away. But there's a price. You have to accept that information can flow backward in time. You have to accept that the future affects the past. You have to accept that causality, as you understand it, is not fundamental. This is where the paradox lives. In classical physics, in everyday life, causes precede effects. You drop a glass, then it breaks. The dropping causes the breaking. Time flows in one direction, from past to future, and causality flows with it. But in Feynman's quantum electrodynamics, this is not always true. At the quantum level, the distinction between cause and effect blurs. Future events can influence past events through these backward time paths. Now you might be thinking, okay, but we never see this in everyday life. We never see the future affecting the past. We never see effects preceding causes. And that's true. On human scales, time behaves normally. The future doesn't reach back and change the past. Why not? Because of interference. Remember, every path contributes, but most of them cancel out. The paths where large objects move backward in time, where macroscopic causality is violated, these paths interfere destructively with overwhelming probability. They wash out. Only the forward time paths survive on average. But at the quantum level, where we're dealing with single particles, individual electrons and photons, the backward time paths don't always cancel. Sometimes they survive, Sometimes they contribute measurably to what happens. And that's why quantum mechanics is weird. That's why particles can tunnel through barriers, why they can be in multiple places at once, why they can seem to know about the future. Because, in a sense, they do know about the future. They're exploring paths that include it. Here's something remarkable. Feynman's approach doesn't just work for electrons and photons. It works for everything. Every particle in the universe, every interaction, every force can be described using this path integral formulation. You sum over all possible histories, all possible paths through space and time, including paths that go backward, and out comes the probability for what you'll observe. This is one of the deepest principles in physics. It's called the principle of least action in its classical form, but Feynman elevated it to a quantum principle. Everything that can happen does happen, and nature averages over all possibilities. Let me show you why this matters beyond just electrons and positrons. Feynman's formulation gave us the tools to calculate processes that were impossible to calculate before. It gave us quantum electrodynamics, QED, the most accurate theory in all of science. When we use QED to calculate properties like the magnetic moment of the electron, we get agreement with experiment to 10 decimal places. 10. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other scientific theory even comes close to this level of precision. And it all comes from allowing time to run backward. From taking seriously the idea that particles can move into the past, that future and past are connected in ways we don't see at large scales. This is what won Feynman the Nobel Prize in 1965. Not just the path integral formulation, but the entire framework of quantum electrodynamics that he helped develop, which is built on these ideas. But here's where it gets even stranger. If antimatter is matter moving backward through time, then we should be able to flip this around. We should be able to describe any process involving antimatter as a process involving matter going the wrong way through time. And we can. Look at pair production. A photon with enough energy can spontaneously create an electron and a positron. Two particles appear from nothing. Where did they come from? Energy converted to mass. Okay, fine. But here's another way to see it. The photon doesn't create two particles. It creates one particle, an electron, that briefly moves backward in time before turning around and moving forward again. The moment when it's moving backward, we call it a positron. The moment when it turns around, we call it pair production. But from the particle's perspective, there's only one particle. It just takes a U-turn in time. Think about that. What we see as creation of matter and antimatter, the particle sees as just changing its direction through time. And when the electron and positron annihilate, turning back into photons, what's really happening? The electron reaches the point where it turned around, and time straightens out again. The loop closes. The particle stops its temporal detour and gets back on the forward path. This is not metaphor. This is not analogy. This is the actual mathematical description of what's happening in quantum electrodynamics. The equations don't distinguish between these interpretations. Both are equally valid. Both give the same predictions. Both describe the same reality. And that tells you something profound about time itself. Now let me tell you the really unsettling part. If electrons can move backward through time, if particles can take paths that connect future to past, what does that mean for free will? What does that mean for the idea that the future is open, undetermined, not yet decided? If the future affects the past, isn't the future already real? Doesn't that mean everything is predetermined? Here's where we have to be careful. Feynman's formulation doesn't say the future is determined. It says the future contributes to the present. All possible futures contribute. Every outcome, every branch, every possibility sends paths backward in time that interfere with the present. And when you sum over all these contributions, you get probabilities, not certainties. Probabilities. The future is real in the sense that it participates in defining the present. But it's not singular. It's not one definite thing that's already happened, and we just haven't gotten there yet. It's a superposition of possibilities, all of which exist in potential, all of which send influences backward. And the sum of all these influences determines what we observe now. Does that mean the present can affect the past? In a sense, yes. If you measure a particle now, you collapse its wave function, you force it to take a definite value, and that choice affects which histories contributed to its current state. You're retroactively selecting which paths through time were real. This is called retrocausality, and it's one of the most controversial ideas in quantum mechanics. Feynman didn't explicitly advocate for retrocausality, but his formulation allows it. The math permits influences to flow backward in time, and nothing in the theory forbids it. Here's an experiment that shows this. The delayed choice quantum eraser. You don't need to understand all the details, but here's the basic idea. You send photons through a double slit, and they create an interference pattern. This pattern tells you the photons behaved like waves, taking both paths simultaneously. But if you measure which slit the photon went through, the interference pattern disappears. The photon behaves like a particle taking only one path. Now here's the twist. You can delay the measurement. You can let the photon pass through the slits, let it hit the screen, and only then measure which path it took. You'd think this shouldn't matter. The photon already hit the screen. Its fate is sealed. But when you do this experiment, the interference pattern appears or disappears depending on whether you make the which path measurement, even though that measurement happens after the photon hit the screen. The future measurement affects the past behavior of the photon. This has been done. This is real experimental physics, not speculation. And Feynman's path integral formulation explains it naturally. The photon's path includes future interactions. The measurement you will make is part of the sum over paths. Future and past are entangled in the quantum description. Let me bring this back to Feynman himself, because understanding the man helps understand the work. Feynman was a maverick. He didn't think like other physicists. While his colleagues were working with complicated equations, drowning in mathematical formalism, Feynman was drawing pictures. He was asking himself, what's really happening? What does the electron actually do? And he trusted his intuition even when it led to crazy places. The story goes that when Feynman first presented his diagrams at a conference, the established physicists were skeptical. These pictures seemed too simple, too childish. Where was the rigorous mathematics? Where were the proofs? But Feynman's diagrams worked. They gave the right answers. And gradually, every physicist learned to use them. Today, Feynman diagrams are the standard language of particle physics. Every student learns them. Every paper uses them. They're fundamental. But what made Feynman's approach revolutionary wasn't just the diagrams, it was the philosophy behind them. Feynman believed that nature is fundamentally simple, that the complexity we see emerges from simple rules applied to all possibilities. He believed that if you can't explain something simply, you don't understand it. And he believed that time is more symmetric than our everyday experience suggests. Think about the equations of physics. They're almost all time reversible. If you have a valid solution, you can run time backward, and you get another valid solution. Newton's laws work equally well forward or backward in time. Maxwell's equations for electromagnetism are time symmetric. Even Einstein's general relativity is time reversible. The universe doesn't care which direction time flows. That's a deep clue that time symmetry is built into the fabric of nature. Of course, we experience time flowing in one direction. We remember the past, not the future. Eggs break, but don't spontaneously unbreak. Entropy increases. The arrow of time is real. But Feynman showed that at the fundamental level, at the level of individual particles, time's arrow is not absolute. Particles can go both ways, and the forward flow of time we experience emerges statistically from the sum over all those backward and forward paths. Here's another way to think about it. In classical physics, you solve for the future by knowing the present and applying the laws of motion. Initial conditions plus laws equals final state. Cause leads to effect. But in Feynman's formulation, you solve for the present by considering all possible pasts and all possible futures simultaneously. The past and future are inputs on equal footing, and what happens now is determined by the interference of all these possibilities. This is completely alien to how we think about time. We think of ourselves as moving through time, from past to future, making choices, causing effects. But from the Feynman perspective, we're part of a four-dimensional structure where past, present, and future are all equally real, all connected by quantum amplitudes, all participating in defining each other. Now, does this mean time travel is possible? Can we build a machine that sends information backward through time? The answer is subtle. At the level of individual particles, time reversal happens constantly. Particles take paths that go backward, that loop through time, that connect future to past. But these paths average out. They interfere. On large scales, causality is preserved not because backward time travel is forbidden, but because forward and backward contributions balance in such a way that macroscopic causality emerges. Could you exploit this? Could you arrange things so that a message propagates backward in time on a scale we could detect? Probably not. The interference is too effective. The cancellation is too complete. Quantum mechanics allows backward time paths, but it also enforces that they don't produce observable paradoxes. The universe is self-consistent. You can't change the past in a way that prevents the present from having been the past that led to the present. That's circular, but it's the truth. The universe is circular in time at the quantum level. Let me tell you about one more aspect of Feynman's work that connects to time. Renormalization. Remember those infinities I mentioned earlier? The ones that plagued quantum electrodynamics? Feynman found a way to get rid of them, not by changing the physics, but by carefully reorganizing the calculations. He showed that the infinities come from including contributions at arbitrarily short distances and high energies, and that these contributions can be absorbed into the definitions of mass and charge. You measure the electron's mass in experiments. That measured value already includes all the quantum corrections, all the effects of the electron interacting with its own field, all the virtual particles swarming around it. So you don't need to calculate the mass from first principles. You just use the measured value. The infinities disappear because you're not asking the theory to predict something you already know. You're asking it to predict new things, and those predictions are finite. This procedure is called renormalization, and it's one of the most powerful tools in physics. But it's also controversial because it feels like a cheat. You're hiding the infinities instead of explaining where they come from. Feynman himself was uncomfortable with it. He called renormalization a dippy process and said it's not mathematically legitimate. But it works. It gives the right answers. And sometimes in physics, getting the right answer is more important than mathematical purity. What does this have to do with time? Well, renormalization is all about integrating overall possible paths, including paths that go to arbitrarily short times, arbitrarily small distances. When you allow particles to interact at every possible scale, including the Planck scale where quantum gravity becomes important, you get infinities. Feynman's path integral approach makes these infinities explicit and shows how to handle them. Time, at the smallest scales, becomes fuzzy, uncertain, mixed up with space in ways we can't resolve with current theories. So here's the picture. At everyday scales, time flows forward. Cause precedes effect. The past is fixed, the future is open, but at quantum scales, time is more fluid. Particles explore paths going both directions. Future and past interfere. And at the smallest scales, near the Planck length and Planck time, space and time themselves might dissolve into something more fundamental, something we don't yet understand. Feynman gave us the tools to navigate this strange landscape. His path integrals, his diagrams, His entire approach to quantum field theory rests on taking time symmetry seriously, on allowing particles to go backward, on summing over all possible histories. And this framework has been so successful that we've extended it far beyond electrons and photons. We use it to describe quarks, gluons, the weak force, the Higgs boson, everything in the standard model of particle physics. Every prediction of the standard model uses Feynman's methods. Every calculation of how particles scatter, decay, or transform relies on summing over Feynman diagrams, including diagrams with loops that go backward in time. This is not abstract theory. This is the tool we use to design particle accelerators, to interpret experimental data, to discover new particles. When the Higgs boson was found at CERN in 2012, the analysis that confirmed it was a Higgs used Feynman diagrams. When we measure the properties of the top quark, we use Feynman diagrams. This is the working language of the field. And at the heart of it all is this paradox. Time runs backward. Particles are their own antiparticles moving the opposite direction through time. Future and past are connected. The universe sums over all possibilities, and what we observe is the interference pattern of histories that never happened but still contribute. Let me bring this to a close because we've covered a lot and I want to make sure the picture is clear. Feynman's Nobel Prize work revealed that time at the quantum level is not what we think. It's not a river carrying us from past to future. It's not an arrow pointing one direction. It's a dimension like space, and particles can move through it in both directions. When they move backward, we call them antimatter, but they're the same particles, just time reversed. This idea solves real problems. It makes calculations possible that were impossible before. It explains why QED works, why we can predict particle interactions with astonishing precision, why antimatter exists and behaves the way it does. But it also raises deep questions about causality, about determinism, about the nature of time itself. Does the future already exist? In some sense, yes, it participates in the present. Does the past change when we make measurements? In some interpretations, yes, we select which histories were real. Is time fundamentally different from space? Maybe not. Maybe time is just another dimension, and our experience of it flowing is an illusion, an artifact of entropy and memory. These are not settled questions. Physicists still debate the interpretation of quantum mechanics, the meaning of the wave function, the reality of retrocausality. Feynman's formulation is agnostic about these issues. It gives you the tools to calculate, but it doesn't tell you what's really happening. And maybe that's appropriate. Maybe the universe is quantum at its core, and our classical intuitions about what's really happening are simply wrong. Here's what I want you to take away from this. The universe is stranger than you imagined. Time doesn't work the way your experience tells you it does. Particles can move backward through time, and this is not speculation. It's part of our most successful physical theory. Feynman saw this. He built a framework around it. And he won the Nobel Prize for showing us that reality is weirder and more beautiful than common sense suggests. You'll never look at time the same way again. Every time you see matter and antimatter annihilate in a particle detector, remember, you're watching a particle loop through time. Every time you read about quantum entanglement or superposition, remember, you're seeing the universe sum over all paths, including impossible ones. Every time you wonder what time really is, remember Feynman's answer. Time is a dimension. Particles explore it in all directions. And we experience only the interference pattern of all these explorations. That's the paradox hidden inside Feynman's Nobel Prize work. Time runs backward. The future affects the past. Cause and effect blur at the quantum level. And yet from this strange foundation, we've built the most precise scientific theory ever created. We can predict nature with 10 decimal places of accuracy by assuming particles time travel. That's not intuitive. That's not obvious. But it's true. And here's the final thought I'll leave you with. Feynman showed us that the universe doesn't care about our intuitions. It doesn't care that time travel seems impossible. It doesn't care that causality feels fundamental. The universe follows its own rules, and our job as physicists, as thinking beings, is to discover those rules even when they violate everything we thought we knew. Feynman did that. He looked at time, really looked at it, and he saw that it could run both ways, and he had the courage to take that seriously, to build a theory on it, and to show that it works. We are living in the universe Feynman described, a universe where time is not what it seems, where particles are time travelers, where future and past are woven together in a quantum tapestry. And we figured this out. Tiny creatures on a tiny planet, using mathematics and experiments, unraveled one of the deepest secrets of time itself. That's remarkable. That's what physics is about. Not just collecting facts, but seeing through the illusion of everyday experience to the strange, beautiful reality underneath.